Hello. Today I want to show you a couple tricks and principles that can be used when analyzing a circuit. Some of these principles will involve a tool called a voltage diagram, a couple rules for writing equations called Kirchoff's current law and Kirchoff's voltage law, and then a very helpful principle about resistors being in series and being in parallel, and some of the differences that those different arrangements can produce. So, first off, I'd like to show you what a voltage diagram is. First of all, just across every single element in a circuit, there's always a voltage difference. And so here in this simple circuit, there's a battery and there's 4 different resistors. And across every single one of these, there is a difference in voltage. The voltage on this side and this side is different. The voltage from here to here is different. From here to here is different, and so forth. Each of these voltage differences is what Ohm's law gives us. If you remember, V equals IR. So if we know the current, we could multiply it by the resistance, and that would give us this voltage difference. Or if we know 2 out of the other 3 things, we can find the third. So anyhow, a useful tool for this is what's called a voltage diagram. And what a voltage diagram is you can label these with letters if you want, various parts of the circuit, but I kind of think of it like chutes and ladders. Batteries help us go up in voltage to some sort of height. I'm not sure what that number is. Actually, I do know what that number is. That's 12 volts. And maybe I'll call the bottom 0 volts. And then this particular circuit has a resistor here. When I go from this point to this point, I had to go down some amount in voltage. I don't know what that is, but I indicate that by going down somewhat to some new level. And then I've got a choice. I can go down through this one, or I can go this route and go down through 2 elements. Either way, when I'm done, the next spot I'll be down is at the bottom. So maybe I'll draw the B to E route, and I might also indicate the C to D route, and somewhere in the middle there's a new voltage. If you'd like, you can actually draw in the resistors in here. And I didn't draw it to scale because I don't have any sort of numbers, but anytime there's a big resistance, that's going to require a big jump. If there's a little resistance, there'll be a little jump, and so forth. But here's kind of a basic voltage diagram. One of our next steps might be then to figure out actual numbers, and maybe we'll have a resistance given to us, or we'll have a current given to us, and we can use this formula to figure out how big of a jump is it from here to here, or across this one, and so forth. Or we could get out a voltage, a voltmeter, and place one end on this side and one end on this side, and actually measure the voltage difference across that. And that would give us this particular height. And we could measure from here to here, and that would give us this one. And we could measure from A to B, and that would give us this one. And the only thing I know right now about those 3 things is that those 3 numbers would have to add up to 12, because that's the only number given to us. But that's a voltage diagram. You'll see some more examples of that as we progress through our examples. So here's another picture of a circuit, and then over here is the corresponding voltage diagram. And so the first step, we went up because of the battery, and then when we went across the 3 ohm resistor, we went down some, and then across the 7 ohm resistor, we went down again. Across the 12 ohm resistor, we went down a little bit more, and the 4 ohm at the end brings us all the way back to the bottom. So I actually do have some numbers here and could calculate how big of a gap there is here and here and here and here by using Ohm's law. Ohm's law says that the voltage drop is equal to the current times the resistance. And so the current is 1.2. And then I actually want to find all 4 of these voltage drops. And so a nice trick on the calculator to do all 4 of them at once is to use a list. So I'll use a brace and separate those 4 resistances with commas. And grab my calculator. Don't have it out yet. So 1.2, and then the brace symbol is second parenthesis. And then you can type your numbers, 3 and 7 and 12, and that was a 4, and second parenthesis. And notice it gives me all 4 of those voltage drops, 3.6 volts, 8.4, 14.4, and if you press over, you get 4.8. So if I fill those numbers in on our diagram, 3.6 and 8.4, and 14.4 and 4.8. And the total voltage of this battery, for instance, would be if I added all 4 of these things together. So you can all retype them in you want, or if you have one of these already in a list, you can go to second list and take the sum of your answer. And the total voltage of the battery must have been 31.2 volts. So there's a voltage diagram, and very common tool that's used to analyze things. Whether you actually draw it or just imagine it, it's still a useful tool. So here's 2 equation makers, I call them, Kirchoff's laws. So Kirchoff's current law is one that we've actually studied a little bit before, that the total amount of current that ever enters an intersection has to add up to the total amount of current that leaves an intersection. So 2 plus 7, the total current that comes out must be 9 amps. Now in a circuit that might be a little harder to imagine because it's not quite as straightforward as what's drawn here, but what I like to do is draw in current in each branch of the circuit. This particular circuit has actually 3 different branches. The first branch, and I'd call it kind of the primary branch, is the branch that goes through the battery. And then that branch breaks into a section that goes down the middle and a section that goes around the edge. And with no numbers, there's not a whole lot I can say about these except for the fact that I can write an equation. The blue current is what goes into this intersection, and the green and red is what comes out. And so I can write one equation right here. That's I blue equals I green plus I red. For convenience sake, I usually don't get out colored pencils and do this, so I often will call it I1 and I2 and I3, and just label that somewhere in my diagrams as I draw them in. So the other equation maker is Kirchoff's voltage law, and it's a little more complicated, but it's a more powerful tool, and really it's no different than the voltage diagrams that you saw just a second ago. It's just instead of drawing that picture, you could write an equation by looking at loops in a circuit. And so basically what his law says is that for every loop in a circuit, the total voltage differences, all the increases and all the drops, must be equal. So you can write 2 different types of equations. You can write all the voltage increases, voltage increase plus a different battery and so forth, and then set that equal to all the voltage drops. Or the technique I prefer is to pick a location and walk yourself around in a loop, and anytime you go up in voltage, you write a positive number or a positive expression, and anytime you go down in voltage across some sort of resistor, you write a minus or a negative number. So let's look at this particular example and see if we can see what sorts of equations we can set up with it. So if we look at a voltage diagram, there are 3 different currents and so forth, so you got this sort of a picture. But what Kirchoff's law says is, let's simplify it by just looking at one specific loop. So if I just look at this loop, and remember this was a 4 ohm resistor, I could write a couple different equations. I'm going to start here, and as I go up through the battery, I increase voltage, so I'm going to write a positive, and I know the exact number, 10. And then I'm going through this wire. I'm not changing voltage, but now as I go down across this resistor, I went down in voltage. And so if I knew exactly how many volts that was, I could write that in. I don't, but I do know something about this. I know that V equals IR. And so I could say minus IR. The I is the green current. I don't know what that is yet, but I can put a variable there. And then the R is 4 ohms. So I could do this. And now I'm down here, and once I get back to where I'm starting from, I'm done with my loop, and I can write equals 0. And there's an equation that I can use. Sometimes these equations are very useful. Sometimes these equations have so many variables in them that they're kind of a waste. But this one is helpful because it only has one variable, the current that's in this green portion of the loop. And so I can solve this pretty quickly and find out that the current in the green loop is equal to 2.5 amps. So maybe I'll write that over here so that I can keep it, not lose that.
Preston Huckabee, high school office. Preston Huckabee, high school office.
And if I want to, I can come up with some more equations by considering some different loop. So let's look at, instead of this loop, suppose I look at this loop. So same basic type of equation can be formed. Starting here, I go up, that's 10 volts up. As I go across, I'm not going through a resistor, so I'm still at 10 volts. And now I had to go down across this 8 ohm resistor. So write that as going down IR. The resistance part was 8, and the current part I don't know, but I can call it I red. And then I had to go down again through a 12 ohm resistor. So I'd write another minus 12 I red. And that's it. Now I'm back to where I started from, so I can write equals 0. And this equation is also a pretty nice one because it only has one variable. If I combine those, I get negative 20 is what we call the effective resistance of these two things. More about that in just a minute. And it doesn't take much to solve this, and you get that the current through the red portion has to equal a half of an amp. And combining these two equations with Kirchoff's law about I green plus I red equals I blue from last time, we can know that the total current through the battery part is equal to 3 amps. So that's Kirchoff's laws. Again, they're useful for making equations, and they're applicable for more than just resistors. When you study more complicated circuits in college or in future classes, you can remember these laws again. So the last topic I want to talk to you about is the specific arrangements of resistors. Resistors can be set up in two really significantly different ways that both mathematically and physically look different and have different properties. One is when they're all kind of connected, one right after another. Sometimes they're called daisy chains together, just boom, 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 in one long chain. If one of these were to go out, they'd all go out. If you remember, a lot of Christmas lights are set up in that form. So one of your Christmas lights goes out, the whole strand's dead. That's being called connected in series. The other technique is when resistors are attached to the same voltage on top and so forth, and they're lined up in parallel. So, and of course the last example had a combination of that. You had series here, and then you had parallelness. But one kind of very useful concept is that you can always find an equivalent resistance. So these three things, you can find an equivalent resistance to this, as if it was just one big resistance. And even when you've got two parallel, you can find one equivalent resistance and simplify this circuit so that it's just a single battery and a single resistance. So just a few facts about resistors being in series versus parallel. When they are in series, all the resistors that are in the chain will have the same current running through them. But because they probably have different resistances, they will each have different voltage drops, which is indicated by Ohm's law, V equals IR. Same current, but different resistances gives you different voltage drops. And when they're in parallel, you have kind of the opposite effect. They're all going to have the same total voltage drop, but because they have different resistances, then they will have different amounts of current through each. The higher resistance ones will have less current than the smaller resistance ones. Now, when you've got them in series, finding the equivalent resistance is very simple. You just add up the resistances. We kind of did that in that last example. 8 plus 12 was a total of 20 ohms. When they're in parallel, you actually add up their reciprocals. And that gives you the reciprocal of their resistance. And so take the reciprocal of that, and that is your resistance in parallel. So let's do a few examples. This first one you saw, 90, 250, 400 ohms. They're all in series with each other. And so to find their equivalent resistance, I'm just going to add them up. That's 90 plus 250 plus 400 for a grand total of, I think that's 640. Make that 740 ohms. And so this circuit, as complex as it looks like, could be simplified and written like this. I've got 60 volts, and on this side I've got 740 ohms. And so the current that runs through this can be found using Ohm's law. It would be 60 divided by 740. So or roughly 0.8 amps. Over here, we can find an equivalent resistance as well, but these are in parallel. And so when they're in parallel, you have to add up the reciprocals and take the reciprocal of that. So I like to write it like this: 1/8 plus 1/18. I'll put it in parentheses. And you could write 1 over that, but when I type it in my calculator, I will usually find the reciprocal button, which is a little -1 exponent. So 1/8, oops, forgot the parentheses, 1/8 plus 1/18, and parentheses, and then the little -1 exponent button that's right here is the reciprocal. Come on. So the equivalent resistance of this circuit is 5.54 ohms. Now I want you to notice here, when you add all these resistances together, you get a bigger resistance. That's kind of intuitive. When it's in parallel, anytime you add resistances in parallel, you will end up with an overall resistance that is actually less than either of the combined resistances. And one way that has helped me to think about that is every time you add another resistor in parallel, you're adding another opportunity, another route for current to flow. That makes overall it easier for current to flow, therefore a lower overall effective resistance. So keep that in mind. Adding a resistor in parallel will reduce your overall resistance and increase current, whereas when you add a resistor in series, you will increase the overall resistance and decrease current. So, one last example that kind of balances all these things and combines them together. I'd like to find how much current runs through the battery portion of this circuit, and do that by finding the equivalent resistance of all of this. We can do that if we add these together. Since these are in series, we can say that this part of it is 20 ohms. And now I've got effectively a 4 and a 20 ohm in parallel. And so I can add them up using the reciprocals. So 1/20th plus 1/4. Oops. And then the reciprocal button. They have an overall resistance of 3 1/3. And so the total current then that runs through this battery must be equal to 60 divided by 3 1/3. So I'll do 60 divided by answer. And we get a total current of 18 amps. So, thanks for watching.